Hi, welcome back to our next video. We have been discussing static indeterminacy of trusses, beams, and frames so far. What beckons us after this? Yes, it is kinematic indeterminacy. This video is meant to give us a flavor of how force method and displacement method works. In particular, we are going to learn it in the context of truss analysis. In this process, we will also get a glimpse of what is called kinematic indeterminacy. Let's try to solve this truss in figure 1 for unknown forces. Is this truss stable by the way? Yes, it is. Though it lacks the usual triangulation in geometry, it is stable because it has four unknown reactions, all right, which makes it externally stable, and members AC and BC are capable of any load applied at this joint, particular joint C. Let's name the unknowns next. They are what? HA, VA, FAC, FBC, VB. Why not HB? Because we see that member BC is vertically aligned and hence only the reactive component VB, right, would develop at B. We can next write down the equations of static equilibrium applicable at every joint. Okay, these are the static equilibrium equations which are applied at every joint. At joint B, we don't use sigma x equal to 0, right? At joint B, we just use sigma Fy equal to 0, all right? So if we consider all equations applicable at joints A, B, and C, we have these five equilibrium equations as listed. So what we see is we have five unknowns and five equations of equilibrium. Therefore, we say this stress is statically determinate and stable, right? Let's now consider AB is equal to 3 and BC equal to 4 meter. We are going to solve this problem with some values of AB and BC. Okay, that's why we do so. So let AB equal to 3 meter and BC equal to 4 meters. This is 4 meters. All right. Figure 2 shows the free body diagram of truss of our interest. That is this truss what we are talking about. There is nothing new here. If you are familiar with basic truss analysis, you can determine as usual the reactive components first using three equations of equilibrium such as sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. We have three equations and three reactive components such as these three, right? So once we find them, we can move to the joint C, right? Once we find these three values, we can move to joint C. We have the member forces to be determined at, fine. If we use the two equilibrium equations applicable at joint C, it's a cakewalk. The joint C is shown in figure 3 with relevant details. Once we determine these two member forces such as FAC and FBC, we are done with solving for all unknown forces as this truss is a determinate one. This is how we solve a problem by force method. However, we didn't learn it completely because only when the truss is statically indeterminate, we get to see how to solve for inherent forces by the force method. But we will learn it a little later. What are we up to here next? When we solve for the unknown forces in a unique way, right? The noteworthy point is the displacements associated with the structure is also unique, right? So one can think of approaching the truss analysis in terms of displacements rather than forces. Okay. So instead of choosing forces unknowns, one can choose displacements as unknowns and solve the problem. In that case, first we need to look at the way the truss deforms upon the application of load, right? That's what we see here in figure 4. When loads P and Q are applied at joint C, only joint C displaces, right? And the deformed configuration of this truss is denoted by this gray dashed line. In x direction, it displaces by U3, right? And in y direction, it displaces by V3 respectively. So if we know U3 and V3, we can solve for the unknown forces as well. We'll see how in a while. If we denote displacements in the x direction by U and in y direction by V respectively, then U1, V1, U2, V2 pertain to supports A and B. That's why in an orderly manner, we named the displacements at joint C as U3 and V3 because for joint A, we are using U1, V1 and joint B, we are using U2, V2. And so in order, we have U3, V3 for joint C, right? These displacements are altogether called global degrees of freedom. Okay, global degrees of freedom is what we say. So wherever I use this DOF, it stands for what? Degrees of freedom. Okay, so in a crude way, we can say, in a crude way, we can say the degrees of freedom is what? Possible displacement rotations at a particular joint. As in a truss, we got only pin joints, rotation doesn't have any relevance, and hence only two translational degrees of freedom called U and V are considered at every joint. Okay, so in a truss, rotation doesn't come into play, so only displacements in x and y direction are to be taken into account at every joint. This particular truss of figure 5, apart from U3 and V3, right, remaining degrees of freedom take a value of 0 each. This ones I mean. Because they correspond to pin supports where these two translations are restrained. Fine. Only in U3 and V3 are unrestrained and hence are unknowns. In the displacement method of analysis, these U3, V3 constitutes the unknowns in stark contrast with the forces in the force method of analysis. Okay. There is also what we call local degrees of freedom. It means the possible ways in which a member deforms, right? The only possibility for a truss in this regard is what? Elongation. Okay, a truss can only elongate or contract or shorten. Here we denote these elongations of members AC and BC by delta 1 and delta 2. We will use them later. In general, the local degrees of freedom for a line element is axial displacement, transverse displacement, and rotation, right? In a beam, what exists? Transverse displacement, rotation, and in a frame element, all three are present. Okay, I mean to say in a truss, only axial displacement possible, and in a beam, transverse displacement rotations are possible, and then in a frame, all three are possible. Okay. At this juncture, we got to install in our minds the basic ingredients of structure analysis. These four concepts are the fundamental ones in structure analysis. First is the stress strain relation. Everyone will be familiar with this in my opinion. Just I want to convey that we consider loads that would not cause the stress anywhere in the structure to go beyond what is conventionally called the yield point, right? That is, we operate within the linear elastic range wherein the Hooke's law holds. Second concept is the equilibrium requirement, which we are familiar with. It mandates that there is no resultant force nor moment applicable to the structure as a whole or to any of its parts. Okay. So we know what is equilibrium condition. Third is called strain displacement relation. This warrants a one-to-one correspondence between the displacements and corresponding strains. We will explore it in detail when it takes the center stage anywhere. Finally, we have compatibility conditions. Okay. What do they mean? These are certain geometry conditions mandated to ensure continuity of the structure. For example, here in figure 8a, we have a beam whose right end is supported on a roller. Therefore, one anticipates the vertical displacement, this displacement at B to be 0. This is the compatibility requirement here. Next, in figure 8b, we have a typical joint of a portal frame. The compatibility requirement here is the angle between the members at a rigid joint remains same even after deformation. Okay, we know that already. And in figure 8c, we have a pin joint of a truss, this figure. Here the compatibility requirement demands each end of members framing into it experiences same displacement. Okay, all members connected to a pin joint experience the same displacement. These details are adequate to solve a truss by displacement method. Let's try to solve the truss in figure 9. Okay, let's mark the local degrees of freedom, that is elongations of members by delta 1 and delta 2, because that's what an axial element is capable of when any load is applied at a joint such as C. Okay, so when we apply a load at this joint C, we can expect these two members to undergo change in length along its own axis. Okay, so we mark them by delta 1 and delta 2. Fine. The first step is we are going to write these elongations in terms of member forces developed in the respective members. Okay, we know the formula already. I suppose it is delta equal to PL by AE. So instead of P, we use the member forces in these two members AC and BC. Okay, So from this, we get these two expressions relating elongation to the member force. Fine. We consider A and E to be same for both members here. From this, we frame these equations given by this one. We need to be aware that when we do so, we already use what? We use stress strain relation and strain displacement relation, this formula PL by A. Okay. What else do we have among the basic ingredients I have talked about? Yes, compatibility conditions and equilibrium equations. The compatibility condition mentioned here is the global degrees of freedom should be consistent with the local degrees of freedom, right? That is the compatibility condition here. Okay, we have this global degrees of freedom. Also, we have this local degrees of freedom. They should be consistent enough to ensure certain geometry conditions. Okay, so here the degrees of freedom at joint C are unconstrained, which are U3 and V3. Their count is called what we mean by kinematic indeterminacy. Okay, so which is true in this case. That is the unrestrained global degrees of freedom for a structure in total, when we count them up, is what constitutes the kinematic indeterminacy. Okay, let's slightly get into the compatibility aspect here with the help of another example before we explore it for our concern stress. This will immensely help understand the way we will develop equations for our problem of interest. In this figure 12, we have a simple truss. When it is subject to a load n at joint B, it is going to deform and take the new position indicated by B dash. We can understand that upon the application of load n, what will happen? The member BC will shorten, right? While the member AB will elongate. In figure 13, we see this indicator in red short lines marked by B dash. That is, the elongation of member AB is given by this BB dash, and the shortening of member BC is given by this BB dash, which are both in red. From the figure 13, one can determine this delta 1 and delta 2. You can relate this with this, and you can write what is delta 1, delta 2. That is elongation for member AB and compression for or shortening for member BC. All right. Now, suppose that you already know these two values of local degrees of freedom, such as delta 1 and delta 2. Okay. From them, can we determine the displaced position of joint B? Yes. How? Take a compass and string an arc with A as center and radius equal to what? Radius equal to initial length plus this delta 1. So when we do so, we get this arc 1, 1. Okay. Similarly, make another arc 2, 2. Okay, with CS center and deformed length of member BC. So with CS center and radius equal to BC minus delta 2, you make another arc which is 2, 2. Now the intersection of these two arcs gives us the displaced position of joint B upon the application of load. Okay, so when we do that, this B dash can be located by this process. Okay, now the important point here is instead of these two arcs, what we can do is we can use tangent lines. Okay, that's what we see in this thin blue color lines of figure 15. If we replace the arcs, which are indicated in this orange color here, with tangents, okay, we get the displaced portion of joint B with accuracy desired. Here, as the displacements are extremely exaggerated, it looks as if there is a considerable difference, right? This is B dash with arc and this is B dash with this tangents. They look quite away from each other, but in reality it doesn't happen so. Because in practice, they don't differ to a significant extent. So the idea here is if we know the deformed length of each member, we can draw this tangent lines which are perpendicular to each member. See, this tangent line is perpendicular to member AB and this tangent line is perpendicular to this member BC. Okay, and we can get the desired result with accuracy required. Now let us go back to our original problem. We said we used already stress strain relation and strain displacement relationship. Next, we are about to include the compatibility requirement. Let's apply what we learned a while ago to this problem. Here we are going to decompose global degrees of freedom as V3 and U3 to implement the compatibility condition. In this context, we are applying only the displacement V3 first. Okay. So we are just going to take this at once, then later we will consider U3. Okay. So that is out of the overall displacements resulting due to the loads applied at joint C, we are taking only V3 into consideration first. Mind that this V3 is a global degree of freedom. Now for compatibility, the local degrees of freedom delta 1 and delta 2 must be such that they meet the geometric requirement involving V3 so that each member's ends move to this new location C in unison. Okay. To achieve this, we need to use the idea of tangents we have discussed a brief time ago. So we assume that we know the delta values due to the displacement V3. That is, we assume that when we know this, when we apply this global displacement V3, we know that elongation that is happening in these two members, and we call them delta 1, 1 and delta 2, 1. Okay. Here this 1 at this top denote the local degrees of freedom due to V3. Later we will do the same with U3 separately, wherein we use, you can see here, wherein we use 2 at the top. Okay. If we know delta 1, 1, we can draw a perpendicular line. Okay. If we know this delta 1, 1, we can go up to this and then we can draw a perpendicular line at the end of elongated line AC. This is same as drawing what? Drawing an arc as we know. We do the same with delta 2, 1, but what happens here is, as this is already vertical, drawing a perpendicular line at the end is needless. Okay, this is already vertical, right? So when we draw a perpendicular line, this goes like this, and the earlier tangent line was like this, right? So the intersection of this gives this new position C, that is the deformed position, right? So from this process, we get the point of intersection as C in blue. That is, if this geometric arrangement is met, then the compatibility between local and global degrees of freedom is established. Now in the figure 18, we have the enlarged drawing of joint C as we see in figure 17. As we know the value of theta here, we can relate the global degrees of freedom and local degrees of freedom straight away. As each member elongated when V3 is applied, we use plus everywhere. Okay, we see that we use plus sign everywhere because when we pull this joint by V3 amount, what happens is these two members both should elongate to occupy this new position C. So we have only plus signs in these two equations. Okay, next we are going to consider the compatible requirement due to the horizontal global degree of freedom U3 alone. Okay, here when U3 is applied at joint C, the important point is member BC, this is member BC, can't undergo a change in its length as it is vertically aligned initially. Okay, so this is already vertical. Now when we apply horizontal load, this can't undergo any change in its length, whereas this will undergo a change in its length. Okay, so application of U3 only causes shortening of AC. You can go back here and see what happens when I pull this joint in this manner by U3. What should happen? This has to come here, so AC undergoes a reduction in its length. Okay, so that's what we see here. Let's say this reduction in length as delta 1, 2. So from C1, right? This is C1 because this is the reduction in length after this application of U3. So now from C1, we need to draw a perpendicular line. Okay, so that it intersects the perpendicular line drawn at the end of undeformed member BC. We already told this doesn't undergo any change in length. So this is the final position itself. From here, we need to draw a perpendicular line. And for this member, we have drawn this perpendicular line, otherwise called tangent line. These two tangents meet at point C. Okay. So again, we construct this triangle C1. We can construct that. Okay. As we see, AC shortens in this case, right? We have already said that this is shortening. We use a negative sign, right? In the RHS of what we write for sine theta. Okay. This sine theta relates U3 to del 1, 2. Okay. Here del 2, 2 is zero as BC doesn't change its length when a horizontal global displacement is effective. Okay. Now what we can do is we have this set and we have this set. We can combine these two effects and get equations 2 and 3. That is, we applied V3 and U3 separately and wrote the compatibility conditions relating local degrees of freedom, global degrees of freedom, and then we sum them up to get these two expressions. Okay. The last equation we must satisfy after meeting compatibility requirement is what? Equilibrium equations, right? Because we said already we use stress strain relation, strain displacement relation, compatibility relation. What remains is equilibrium equation. If we consider the equilibrium of joint C, this is the truss under consideration. If we consider the equilibrium of joint C in this figure 20, we can get these two equations mentioned by 4 and 5. I'm writing the equation once again here. That is equation 1 is written here again. We had them already, which relate the member forces to local degrees of freedom. Next, we are substituting these two equations, right, in equation 1, in this set of equations. Okay. So when we do so, what happens is we get equation 6 and 7, which relate member forces to global degrees of freedom, right? That's what it did. Finally, we substitute equations 6 and 7 in equations 4 and 5. Okay. So when we do that, what happens is we relate what? We relate the globally applied external loads to global degrees of freedom. Okay, that's what is happening here when we make this substitution 6, 7 in 4, 5. We see that the globally applied loads are related to global degrees of freedom, which are U3 and V3. Okay. Now these two equations can be written in matrix form as we see here. Okay. So when we do that, it gives a system of form K into U equal to P. Here K in this equation is called what? Stiffness matrix. One can invert it and determine what is the displacement vector. Okay. The important point here is we solve for the unknown displacements U3 and V3. Once we know them, we can determine the member forces from these two expressions. Once we know U3, V3, we can get back the member forces. If we do so, we will get same answers as we obtained earlier by saying what? By saying we solve for forces directly, treating forces as primary unknowns. Okay, that's what I'm trying to say is once you know displacements, you can get the member forces, and those member forces will match with what we already found the earlier stage using force method of analysis. That is, we solve for only reactions and member forces. Okay, so this answer and that will match. Due to time constraint, we are not proving here that those forces will be same irrespective of whether we treat force or displacement as unknowns. Okay. From this example, what we learned is if we choose displacement as unknowns, one needs to know what is the degree of kinematic indeterminacy of the structure. We are going to explore the kinematic indeterminacy in the upcoming video, but why should we take this much trouble to solve this statically determinate thrust by displacement method? That's a good question. We see that if we are concerned about just forces, we can solve the problem by force method, avoiding rigor by not choosing the displacement method. But consider a truss as the one in this figure 23. In this case, one finds a static indeterminacy as how many? 6. So if one chooses force method of analysis to solve this problem, there are 6 unknowns to be determined. But the kinematic indeterminacy is merely 2. Why? Because only this joint is allowed to translate in these two directions. Okay, so the kinematic indeterminacy in this case is 2. Not only that, displacement method can be implemented in a simpler manner than how we discussed it here. It means if we solve this truss in figure 23 by displacement method, it is easier to accomplish it. Okay. So depending on whether static indeterminacy is lesser or greater than the kinematic indeterminacy, one needs to judiciously choose the method of analysis. We will discuss the kinematic indeterminacy in detail in the next video. This video is just a primer to the same. Okay. Thanks a lot for your passionate listening. We'll meet again when we discuss the kinematic indeterminacy.